I'll be showing an implementation of Grover's algorithm to solve the maximum clique problem. So this is our agenda. I'll talk about the introduction, the algorithm outline, the implementation, the quantum cost, and hardware usage, and then finish up with the conclusion. So a maximum clique of a graph is its largest fully connected subgraph. This is an important feature of some graphs and fields related to data mining, network analysis, and social networking analysis. This problem is hard because it is computationally expensive. Given that each vertex is either in a subgraph or not, there are 2 raised to the magnitude of v subgraphs of a graph, where the magnitude of v is the number of vertices in the graph. So quantum computing offers computational speedups that cannot be achieved with classical computing. Grover's algorithm can search an unsorted list in square root of n steps, where n is the length of the list being searched, and classically this takes O of n steps to search an unsorted list. And Bochik explains the general steps for a quantum algorithm, and we complete the implementation. Next, I'll show the algorithm outline that Bochik defines. So Grover's algorithm can be used to solve the maximum clique problem using the steps shown here. So first, you have to define k as the minimum allowable subgraph size and x as the subgraph. And then you define an oracle function that flips the target qubit if x is a clique and its magnitude of v is greater than k. Next, you initialize x to a superposition of all of the subgraphs. Then you run Grover's algorithm for the square root of 2 raised to the magnitude of v steps. Remember before, that's the number of possible subgraphs. Then you measure x, and if the outcome is a clique with the magnitude of v greater than k, you store the subgraph and set k equal to the magnitude of v and return to step 2. And if it's not a clique with magnitude of v greater than k, you return the stored subgraph as that is the maximum clique. Next, I'll show the implementation. So to implement the steps from the previous slide, an OR gate using quantum gates needs to be implemented. This is done using De Morgan's law and using a Toffoli gate as a logical AND gate. As the figure shows, Q2 equals Q0 or Q1. Although Bochik provides an outline for using Grover's algorithm to solve this problem, Bochik does not state how to do this. Bochik only states to define an oracle function that flips given the properties of the base. Once this oracle is defined, the rest of the implementation is trivial. Starting with the example graph shown on the left, we can see that there are 3 vertices, edges AB and AC, and it has maximum cliques of AB and AC. The encoding shows that Q edge, right here, and Q edge encodes the graph's edges, and Q vert encodes the subgraph being examined by the oracle. Hadamard gates are applied to the qubits in Q vert to create a superposition of all of the possible subgraphs, so the oracle function can take advantage of the quantum mechanical property of superposition and operate on every subgraph at once. So first, the oracle needs to determine if the subgraph is a clique. And we have 7 groups of levels. The first group of levels encodes the graph and then puts the X gates for the quantum OR gate we'll see later on, and it puts Q-vert into superposition. The second group of levels lists all the edges if the subgraph is a clique. The third group of levels inverts the possible edges and then applies the X gate for the quantum OR gates later on. As you can see, this is a double X, so it is not actually necessary to do the third group of levels. The fourth group of levels are the Toffoli gates from the quantum OR gates, and the fifth inverts Q check edge again and finishes the OR gates. And the sixth group, or the sixth level, applies a multiply controlled Toffoli gate to the output into a single qubit, and the seventh measures the results. It's easiest to use an example to understand this part, so let's assume AC is encoded into Q-vert, and the numbers in red show this assumption. So as we can see, we have A, B, C, and only A and C are 1s, So the only possible edge that would exist if this were a clique would be edge AC, which is encoded here. We invert it, and then we OR it with the encoded subgraph, and we have 1, 1, 1 on the output. And then once we apply a multiply controlled to fully gate, we get a 1. And this shows that the output, or that the subgraph encoded into qvert is actually a clique. And we can show that with a non-clique example, so BC, which as we remember from before was not a clique. We have BC encoded into here. The only possible edge would be BC. And after our quantum OR gates and our multiply controlled to fully, we can see that it's not a clique. So then we see the simulation results. And we have, for our qubits shown here, we have whether or not it's a clique, and then C, B, A. And as we can see, subgraph BC and ABC are not cliques, but all of the other subgraphs are correctly cliques. So at this point, the subgraph is a one-hot encoding. The number of ones in this encoding is the size of the subgraph, and to use an integer comparator, the number of ones needs to be counted, and the output is in Q count, and we can use a full adder to do this. And once the number of ones is counted, we can use an integer comparator to determine if Q count is greater than or equal to K. Then we put the output in Q answer. So this is our quantum full adder. As we can see from the truth table, the sum and C out are calculated correctly with this circuit. And now we have the oracle to determine if the subgraph is a clique and if it's greater than or equal to K. So as we've seen before, this portion, levels 1 through 6, determine whether or not the subgraph is a clique. And then we have our full adder, we have our integer comparator, and we use it to fully gate to act as an AND gate on the output and the integer comparator. So this determines in Q answer whether or not the subgraph is a clique greater than, with magnitude of V greater than or equal to K. And these are the simulation results when K equals 2. So as we can see, only AB and AC are cliques with magnitude greater than or equal to, or with the magnitude of V greater than or equal to K. So at this point, we have to reverse the oracle to return all of our ancilla qubits to 0. And then once we add our quantum diffuser and put the target qubit in the minus state, then we have our complete Grover's algorithm implementation. And these are the simulation results. When we have, so as we can see, the only measured outcomes were AB and AC, which is what we expected. Next, we have the quantum cost and the hardware usage of this algorithm. So the quantum cost of this circuit is in the form of the number of qubits required and of the number of levels required. The depth of the circuit grows more quickly than the number of qubits, but they are both O of magnitude of V squared. Next, we have the conclusion. So in conclusion, we presented an implementation of an oracle for Grover's algorithm to solve the maximum clique problem. The algorithm follows the outline that Bochik defines. The circuit was implemented and simulated using Qiskit. The results showed that the algorithm was successful, and the quantum cost of this algorithm is quadratic, with both the number of qubits required and the depth of the circuit, where magnitude of V is the independent variable. These are some of the references mentioned in this presentation. Thank you for listening, and are there any questions?
Oh, great. Thank you, Andrew. Of course, if anyone has any questions, please add those into the chat. I had one question in that you were looking for subgraphs that were cliques as a property. I'm curious if you think the idea could extend to other graph properties. You know, the one I was thinking of is if I were looking for a cycle within a graph, for example, if that's an, I mean, is there an idea there, you think, or is this maybe specialized to the cliques?
So Cycles, I played around a little bit, trying to use Grover's algorithm with cycles and graphs, and I couldn't really figure out an easy way to extend this work here to apply to cycles, but there are a few other problems that this more easily extends to. But yeah, not cycles.
Okay. Well, no, thanks, Andrew. Maybe one last question. In the chat, Srinivas asked, does it solve the problem exactly?
So there will be uncertainty, as with every quantum problem or every quantum algorithm we have right now. But given or assuming that it does work perfectly, yes, it will always solve the problem correctly.
Okay, in the sense that it doesn't give you approximate answers, it gives you the actual answer. Yeah.
Correct. Yeah.
Well, hey, thank you very much, Andrew.